Okay, so welcome to the AIFI webinar, right? Every 6 months, we organize a research seminar in which we discuss some of the things that some of the relevant figures on quantitative finance and artificial intelligence finance are working on. And so this is 31st of May. And we're very excited to be back again with all the crowd. We've had very good attendance in the previous webinars, and we think we have very interesting topics to discuss this afternoon, right here. First of all, so let me talk a bit about our institute for the ones who are not maybe familiar with it, and I'll discuss it quickly about our bootcamp that we offer, and then we'll have two interesting talks. I'm going to be talking about equity fundamental, equity factor models using machine learning, and Professor Dixon is going to talk about deep partial least squares, right? So we have a very interesting afternoon ahead of us. Okay, so very quickly about us, a little bit of a commercial. So we are an institute where we created the institute in 2018. The idea was and is to offer training for basically quant finance people, right, and also some data scientists, financial engineers. So basically the application of artificial intelligence, investment management, capital markets and risks. And in order to do that, we offer every year a couple of bootcamps, summer bootcamp and winter bootcamp. And there we cover what we think are the more relevant aspects of the theory and implementation of these AI techniques, machine learning, deep learning, and natural language processing in finance. And in order to do that, we think we have, we've gathered, we're a group of people that actually is teaching and practicing AI in finance in top institutions, right? We also working extensively on research. So we do really think that the best thing to contribute, or the best way to contribute to the quant finance community and AI in finance community is actually to some sort of produce open source research, right? And we've wrote a series of papers, and obviously all the professors and advisory board members are producing lots of papers, as obviously, for example, Matthew Dixon, who's already in the audience. So the main idea of the institute is trying to write and teach about finance overall, right? So we're interested in problems like time series prediction, right? So we've wrote a series of papers about deep learning using LSTMs or using GRUs or using NBITs or using deep signature models, which is a paper that we recently released, and also we've been some sort of working on the shape of performance curve, rational time series, deep reinforcement learning. Right, I'm gonna talk a bit about deep reinforcement learning or reinforcement learning in my talk, and also ESG aspects. And we'll soon have a paper published on the Journal of Financial Data Science, FINEAS, Financial Embedding Analysis of Sentiment, which we wrote along with Asir Gutierrez, Peter Coleman, and Jordi Armengol. And there we created an NLP model to measure sentiment using sentence word instead of traditional bets. So using so that's the main idea of where we are busy every day. right? And I funded this again almost 3.5 years ago, and we're still very excited about delivering this content along with really top professionals and academics on the area, like Matthew Dixon, who's with us tonight, this afternoon, and Peter Colm, who's Quan of the Year, but both Matthew and Peter Colm are Quan of the Year, right? So, so we have a really distinguished members of the Quant Finance community. Gordon Reader, who's been previously, right, Quan of the Year, one of the most avid, some sort of authors in the area. Marcos Lopez, who everybody also knows about his huge contribution to ML in finance and quant finance. We have Daniel Schmidt. We have Stefan Jansen, who's teaching the deep learning. The deep learning staff, also author of a couple of books on machine learning in finance, and Tim Loong, who's at University of Washington, and so on. So we offer the summer bootcamp in almost 3 months, right? So it's from the 8th to the 13th August. So in New York, at NYU Tandon in the Metro Tech Center. So we're offering a 6 day intensive training on all these topics. So we just very quickly, so we start looking at obviously Python, but what is machine learning modeling overall? How do we need to pre-process model selection? Obviously, a review of the traditional time series model, linear fractal models, which I'm going to talk about in a few minutes, portfolio allocation, and we're also adding this year a little bit of stuff or we're working on very exciting stuff on option pricing and rough volatility. Then we'll continue seeing the second day deep diving on supervised learning algorithms, right? So for vector machines, trees, key nearest, right? So some of the most traditional machine learning algorithms. And then we'll see unsupervised learning, who's well, one of the most interesting techniques that can be used in finance. At the beginning, you don't think it's important. Then you see how really important can be, for example, variation autoencoders, right? In some of the most important quant finance stuff, right? Then well, the third day where we start digging on more on trees, which are xgboost and obviously ensembles and so on, and some of the most important and successful successful machine learning algorithms for panel data. Right, we're going to be using that also in my presentation today. We'll have also, right, distinguished speakers like Tony Guida, and also the coding modules, right? Nicole Konigstein is going to be offering these. On the day 4, we'll have a really intense deep learning day. Stefan Jansen, Gordon Reader, and Matthew Dixon. So we're going to see here really a very interesting day on deep learning. Day 5 is going to be the reinforcement learning day, and Saturday it's no time for rest, because we actually gonna do natural language processing with me, Ting Hao, Richard, and we'll conclude with an Igor Halpering speech. So we do think it's a really interesting bootcamp I'm offering. Okay, so. And yeah, and then there's the evaluation, right? There's a theory exam, and then there's a project, right? So and then if you pass both, with you, I think you can, right? If you work hard, you attend the bootcamp, right? And then you'll have the AIFI certificate. Okay, so that concludes the commercial, right? So any question? Okay, so let me move on to research, right? So, okay. Good. So, okay. So basically, So let me use, right, around 25 minutes, right, to some sort of discuss, explain a work we recently did with Vincent Zunekind, right, myself. Vincent is a senior quant researcher at ADIA, at Abu Dhabi Investment Authority, and the idea of this paper, that it's still not the preprint still not ready, but it will be soon, maybe next week, right? So we're finishing the preprint, and then you'll have there to read. So we kind of try to answer the question that obviously also previous researchers have been trying to answer, right? Which is, okay, so we have a set of mathematical techniques and some sort of practitioner techniques to work on factor models, right? And these are typically linear, right? So linear factor models. This is something we've all learned in our MFEs, Master of Financial Engineering, or in our finance training, right? From a French stuff and Barra stuff, and so on and so forth, right? So, and we're trying to answer a question, which is, can machine learning models some sort of improve, right, this traditional, right? And a question, by the way, that, as I said, that many other researchers like obviously Matthew wrote a paper, Matthew Dixon, Deep Factor Models, or Tony Guida, which he wrote a book about ML factor models, which I highly recommend. So our work is a little based on using the same data set that was used for in the ML factor by Tony Guida and Guillaume Coqueret. Okay, so the idea, so Vincent and I were, the motivations are, well, what are the motivations for factor models, right? So we know, I'm sure everybody knows in the audience, but just to quickly, right? So we use them for a bunch of things, right? One obviously is in order to do alpha search, right? So we want to some sort of be able to estimate or compute expected outperformance, asset pricing, expected P&L, right? So here we're predicting. Some other factor models are meant to somehow describe, like for example, from a French kind of factor models, right? And also to do multivariate estimation, and we can also use them to some sort of improve portfolio optimization, right? So that's one of the reasons factor models are incredibly useful for asset management, are incredibly useful also for quants, right? So many quants are working on factor models, and certainly Vincent and I have been working professionally on these factor models. You know, when we teach about these factor models, we always say, okay, there are three types of factor models: time series or macroeconomic, the CAPM kind of factor models, cross-sectional fundamental factor models, in which we have you know, features of stocks, right? And we want to perform this modeling. So capital X, the set of random variables of n dimension, A of dimension n, B Z, n is dimension n by k, Z is key factor variables, so to speak, plus U of dimension n, right? So this is basically the and we're going to be using our research is about forecasting returns. So we all know that the way we manage portfolios is we first the first thing we do, or we have to do, as Markovits told us, right, in model portfolio theory, he said, okay, all you have to care, right, it's about a vector of expected returns and a covariance matrix, right? So, and if you know these two ingredients, then you perform, I mean, variance optimizations, you can find optimal portfolios. Okay, so this is the theory. We all know that this is really hard to do, and it's really hard to, especially in the short term, it's really hard to forecast returns, right? And it's also really hard to forecast the covariance metrics, right? So that's why we're here after all these years. Quants are still working hard. Quants and non-quants are working really hard in these difficult markets to forecast returns and covariance matrices, and then try to find what is the best portfolio, right? So y is equal to alpha beta x plus epsilon, and then we use this y hat, right? So the estimate of these returns to perform an optimization, right? And the main goal is to find out the weights to maximize, right? We have actually three ways, right? As we know, three equivalent ways to do portfolio optimization. One is which you do risk minimization, right? One in which you maximize return, and one in which you some sort of optimize risk aversion portfolios. So all three are equivalent. Okay, so the idea is, can we use a set of factors, right? Or researchers, practitioners having asked themselves, right? So can I use a set of factors, right? That in order to forecast returns. So obviously there's and then build an investment strategy. So this is what we're going to investigate here, right? And obviously there's another way to forecast returns, which is using time series, which is a problem that we have investigated in previous papers, and obviously it's another open problem. All of these are open problems. No one have found but obviously, right, many people like Fama French or Litterman or Carhart or many other researchers have done a really fantastic job on factors. So okay, and also Matthew with his paper. So what we're gonna do is we're gonna pick from the book Machine Learning for Fractal Investing, which I highly recommend, from Leon Coqueret and Tony Guida. So they have a data set that has 1,200 stocks, and has monthly data from 1998 to 2019. So what we're gonna do is we're gonna train the algorithms, right, from 1998 to 2016. This is gonna be somehow the in sample, right, in which the algorithms are gonna learn the weights, the biases, and we're gonna investigate hyperparameter optimization, and then we're gonna use them from 2016 to 2019. We will be updating the results with more recent data, but we think this is a somehow obviously interesting period, right, from 2016 to 2019, and we have 100 factors, 100 features: momentum, earnings, yield, quality, and so on. So you'll see the description on the paper. But this is, and by the way, the data set is a Quandl data set, right? Just to credit where it's due, right? So it's a Quandl data set. So we did a little bit of data preparation. We uniformized the predictors. The target was 1 month forward returns, right? And we also, other things need to be done: discretize, remove outliers, remove average values, and so on and so forth. So you'll see all the details of the pre-processing in the paper, right? So it's a matrix of containing all that information. So these 1,200 stocks, and then 100 features, right? And these 20 years of data. So this is some sort of our raw ingredients for our models. Okay, so we investigate here several things. So first of all, right, obviously a lasso model. This is what we all think. This is we want to create a robust linear model, right? So that's what we use: lasso and a linear regression, right? So this is how everybody started, right? And we see it's still a model that obviously it has lots of merits, because it's interpretable, right? You can actually with lasso regularization, some sort of have a limited number of variables, so the degrees of freedom can be small, and then be able to interpret and so on and so forth. We also investigated some other thing that it's not maybe as seen in the literature, which is we used constrained portfolios, right? So I think that's really interesting piece in the paper. It's some sort of what happens if I have constraints on the factors, right? For example, betas being positive, right? And we did a lot of work on this, on trying to constrain the betas, right? So typically, quants working in that space, right, in order to interpret the factor model, say, okay, I want clear relationships from my betas to the result of the model, right? So I want that if ROE is higher, the beta is positive, right? Or if the leverage is higher, maybe the beta is negative, and all that kind of stuff, right? So portfolio managers will not be happy to implement a model in which they don't understand the coefficients, right? So one idea that modelers have put together is this idea of, so let's constrain the betas, right? And there's in the paper interesting elaboration on why, on how we can constrain the betas in a linear regression. Next, we said, okay, so let's use nonlinear models, right? Which is obviously one big question mark, right? Can nonlinear models, and obviously we're not the first ones who tried to answer these questions, right? But we said, okay, let's investigate if what happens if we use some sort of a deep learning model, and here we're going to use some sort of vanilla MLPs, multi-layer perceptrons or feed-forward neural networks. This is panel data, right? And obviously, right, we should use some sort of in other exercises. If it's a time series data, you use LSTMs or use alpha RNNs like the Matthew Dixon papers, right, and so on. So we have a set of neural networks that can be used for time series. But here we have panel data, right? So we're going to be using MLP, multi-layer perceptrons, right? And the details going to find them in the paper. And then we did the fourth thing that was some sort of what we call RL. Right, so obviously, right, RL, everybody has different definitions of RL, right? But the idea of, can we just use neural networks to pick features, right, and the stocks, and say, okay, I want to optimize the information ratio, okay? So instead of, first of all, predicting returns, putting together a portfolio and looking at the results, can we just go straight and try to optimize the information ratio of a portfolio? So some sort of a model-free, right, RL exercise. And the answer is yes, right? So the answer is yes, you can do that, right? When we're not claiming, we will not be claiming in the paper that you actually should do that, right? But this is again, one of the benefits of using neural networks also that you can some sort of ask them to try to do themselves the task of predicting and optimizing a portfolio, right? Okay, because obviously there's a lot of open questions about how we do portfolio management these days. Should we first use supervised learning and use MSE or MAE as evaluators of performance, then use the best predictors and as a vector of expected returns, and then using more portfolio theory or Black-Liederman or other approaches. Okay, so let's move on. Okay, So yeah, so maybe what I'm going to do is given that we have some sort of not a lot of time, you'll find in the slides, right? We actually show the code, right? So we'll have the code that we used, right? Or snippets of the code we use, right? But the lasso is obviously a trivial implementation, so it's not hard, right? The constrained regression, right? You'll see the details in the paper. It's a regression in which you actually say, I am interested in betas that are only positive, okay, and not betas that can be positive and negative, and so on and so forth, right? Because obviously, when you do factors, some of the factors might have negative betas, right? And again, we want to be some sort of using betas that make sense for the practitioners. Okay, and we'll see, and I'll show the results in a second. So this is yeah, how we enforce the idea of signs, right, of these coefficients of the linear regression should be positive, right? And on the linear, right, we kind of work with different architectures of neural networks, and we finally found that this was a good candidate, right, using PyTorch and this architecture. Obviously here, right, you don't need a very large neural network with lots of units, or right, but this is obviously an open point, right, as to whether, right, you should, what is the optimal architecture. But we did a lot of work on trying to find, and we save you the details of that. Okay. Okay, so, and then we develop a series of, you'll see in the paper that we've developed a series of different tests, right, to somehow investigate different features using copulas, right? So one interesting thing what we do in the paper is using copulas to interpret the different factors, okay? So, and I think this is really interesting. So we developed 3 ways to actually look at, to try to explain the relationship between the different features and the target variable. Okay, so these are the results. So let me spend a few minutes here, right? And okay, we tested long, short, and long only strategies, right? And one important thing is that actually unconstrained, right, was delivering pretty good results, right? So linear unconstrained, not necessarily not using lasso, right, but unconstrained, right? It's giving us a high information ratio, right, but a high turnover. Okay, so this is and then when we go nonlinear, right, well, you would say that one of the important aspects is that turnover some sort of gets much lower, right? Especially when we use this information ratio, which is basically the reinforcement learning implementation of it. So the neural networks are actually directly, right, directly meant to optimize information ratio, right, instead of MSE, right, and then putting together a portfolio. I skip the details of but these portfolios are put together using quintiles. Okay. Yeah. So this is well. So this is the main results. So the main results is not the nonlinear models work well, right, compared to linear models, but unconstrained and not using lasso is but at the same time is having a very high turnover, right, compared to other models. And the RL models, or what we call here AR, right, in a linear version and a nonlinear version, offer some sort of a very probably the best combination of all of them, right? Are we claiming that you should use directly neural networks to do you know, we will not be claiming that, right? Because okay, so one of the reasons practitioners want to some sort of do a sequential, right, or what I call sequential portfolio optimization is that, again, you first estimate the returns, then you estimate the covariance metrics, then you do portfolio optimization, and then there's an additional step, right, which is obviously you need to take care of the market impact, which we haven't here, right? Okay, so instead of doing that, right, the neural networks are doing that and doing everything, right? So, and obviously, right, we still don't know, right, and we will be investigating that, how these neural networks actually, right, work, so to speak, in that sense. So this is some sort of fully non-parametric way to investigate the maximization of information ratio, okay, which is again very appealing, but yeah, but less transparent, so to speak, okay. Okay, so again, this is a reinforcement learning problem, right? So here better defined, right? We do not optimize for return, but the final goal is the performance, and we limit overfitting using mini batches, right? So obviously, right, everybody that has tried reinforcement learning in a portfolio management optimization setup knows that there's quite a lot of tricks that you should use to some sort of make it converge and so on, right? But and obviously that's one of the challenges when using neural networks, right? That sometimes you know, you have dots and question marks on the convergence of the algorithms. So this is one thing that you should really investigate. Okay. And this is basically, yeah, how the reinforcement learning model was put together. We were actually debating, right, today, right, as to whether we should call neural networks doing everything an end-to-end model or reinforcement learning model. Obviously, there's a lot of definitions of reinforcement learning. One says that the definition of reinforcement learning is that you should consider systems that had feedback. So obviously here there's no feedback, so this loop, so to speak, right? So you have what the agent does doesn't impact, right, the states, right, in the sense that, right, obviously it impacts your performance, but it doesn't impact the states of the of the world, so to speak, right? But we thought that it was good to put reinforcement learning in the sense that here neural networks do two things, right? An unsupervised learning exercise and then an optimization, right? And I think this is not to exaggerate to say that this is reinforcement learning. But anyway, so the whole idea is that neural networks are asked to produce the best portfolio possible with all the data set at their disposal. Okay, so that's the okay. So there's a lots of things that we can say, and the paper is going to be a little bit of a long one, right? So there's a lot of question marks. So about the data preparation. So people working in factor models know that that there's a lot of work that you should put in data preparation. So there's a lot of question marks as to whether you should get rid of the outliers or not, and so on and so forth, right? And results might be different if you've done different data pre-processing. So that's the point, right? Lasso is always an interesting thing to do. Constrained regression, we think it's an interesting thing to do because practitioners, right, will ask you, let me interpret those betas, right, those coefficients, right, and if some indicator that is meant to be good for stocks is up, returns should go up, right? So that's one of the things you want to, right? So to some extent, again, you want to enforce the signs of the betas, right? Or at least see how enforcing these signs is changing the results. Nonlinear models is when you do neural networks. By the way, I didn't mention, but we also compared that to xgboost, right? So in the, just a sec. Yeah. So you have also the xgboost. Actually, the xgboost is also, very decent model, right? For that, right? And xgboost, it might be a really fantastic candidate to deal with somehow these kind of problems in which you have a variety or some sort of a set of heterogeneous features, right? Outliers and so on. You would say that xgboost is really a good candidate to be used in here. And obviously, Tony Guida and Guillaume Coqueret, they claim that this is the best model. We do think is a really good model. We actually see that it just really creates a lot of turnover, right? At least in our implementation, which we all know this might not be especially good, right? Okay, so what else? And this idea of again, I'm not claiming that reinforcement learning is the thing you should use or you have to use, right? Because of this loss of understanding of what's happening in each step, right? But we do think the more we know about model-free reinforcement learning approaches used that are scalable to many stocks, I think this is going to contribute to our understanding of what's really going on in portfolio management, right? And yeah, so then there's other things that could be, right, implemented as transaction costs or drawdown, right? So no portfolio management exercise is finished without taking into consideration transaction costs, right? A market impact, and there's a huge literature, and this is also a hard problem, right? If you use nonlinear market impact, then things are not quadratic anymore when you try to, right? So, and you have to estimate and so on and so forth. And then, yeah, maybe ideas like having a portfolio optimization as a layer, right? And so on and so forth. Okay, so this concludes my presentation. So again, the preprint is going to be ready, right, next week or in a couple of weeks, and then we're happy to, right, have your feedback and ideas and explore, right. Okay. So maybe let's move on in order to, right, to somehow do things quick. Let's move on to Matthew's, to Professor Dixon's.
Okay, thanks very much, Miguel. Okay, so you should see my slides now.
Yep, that's perfect. It's on screen.
Yeah, thank you.
Okay, great. So how long do we have here? About 20 minutes or so.
Yeah.
30, 45, we're,
okay.
Right, it's really up to you, right? So, but maybe max 45 minutes, right? So we don't, yeah, but take your time, Okay,
I'll try to be considerate of everyone's time here. So, so thanks again for the opportunity. Thanks, Miguel, for that very interesting description of his research. And in fact, what we're going to talk about today in many ways overlaps. This is very recent work. The paper is coming out next few days. There's already some code for this available at the bottom in the GitHub repository in Python using TensorFlow. And this is joint work with Nick Paulson at Chicago Booth and one of my students in data science at Illinois Tech. And this research is kind of interesting because no one has quite cracked this problem properly. And the punchline is that I think deep partial least squares are the answer to a 50-year-old problem in factor investing. So let's see if I can try to persuade you if you are already familiar with factor investing. So I think one of the challenges, and I've been involved with this, asset management firms have reached out to me and asked me to sort of consult with them, and they've had a lot of difficulties reconciling deep learning with the more traditional field of factor modeling, especially fundamental factor modeling, where there's a lot of extra sort of goodies in the model that deep learning doesn't seem to provide. So in particular, they're really looking for a sort of a palatable approach. They're not really wanting to spend a lot of time trying to interpret the models in the way that deep learning has been sort of interpreted by the computer science community. They're looking for a way to interpret it in an investment sense, in an equilibrium asset pricing framework. So what we're going to do is, in fact, cast the factor models into an equilibrium asset pricing framework. And that's going to give you a lot of interpretability for investment. We're going to see, for example, that when there are gains over the risk-free rate, that those are attributed solely to exposure to latent risk factors. After all, an investor should be compensated by their exposure to latent risk. And if they're not exposed to these systemic risk factors, then they shouldn't be getting any sort of risk-free gain, right? That's the fundamental principle of no arbitrage. And so we're going to show how our approach ultimately solves this problem. But in general, I think there's just a lot of issues that have to be addressed. Capturing outliers in the returns, which just aren't being explained by the input, by the predictors. There's issues of interpretability, which factors are more important. There's issues of how to tease out the nonlinearity, the interaction effects, the seconding of the Hessian, off-diagonal Hessian terms. And ultimately, what interpretability means in this field is not explaining what each neuron is doing in the network. It's rather explaining how the model decomposes the predicted returns into explainable and unexplainable components. And then an investor can then hedge away some of those explainable components. So the model has to have utility. It can't just be purely a game of horse race of just which is the best model for our sample prediction. There's a lot more to this as we'll get into it, and the subtleties, which admittedly even I overlooked when I first worked on this problem a few years ago. We also don't assume complete markets and do not assume Gaussian returns. That's really the whole premise for using nonlinear methods, deep learning methods. There's a theory of what's known as Stein's lemma that says if the returns are non-Gaussian, then you need essentially nonlinearity in your regression model. And so we're going to show how, in fact, we've already shown in earlier works that deep learning automatically captures nonlinearity. You don't need to think about which nonlinear terms to add in an ad hoc way, which is a combinatorially intractable problem as you increase the number of features or predictors. When I say features, I also mean predictors. I'll also use the word covariance. This is just sort of econometrics jargon. So apologies for that, but we're sort of spanning multiple disciplines here, from computer science to econometrics. We want to identify and assess the material impact of what is not being captured by, say, linear or quadratic parts in the model. In other words, what are the higher order effects doing, third order, fourth order, in explaining these outliers? That's something that no one has done so far. And then we want to look at identifying the most important factors as the observable factors. And the problem we run into with deep learning is there's no way to map to essentially reveal the latent risk factor attribution, the exposure to the systemic factors, which are sort of inherent in the model. In other words, how much, when I project my input data, which is firm characteristics, onto these systemic risk factors in my deep learning model, how much of that is, how does that work? There's no setup for that if you just do a standard prediction problem in a very mechanical way. So what we're going to show with our DPLS model is that projected least squares is actually the right setup. We can take into account the input data. We can also take into account the asset returns, so the Y and the X. But we project onto a lower dimensional latent factor space. It's a bit like PCA, except now it's now supervised PCA. Autoencoders, as you know, are unsupervised or semi-supervised. They're not supervised. There's no way to incorporate the Y and the different Y and X in an autoencoder. So the bottleneck architectures are useless here. And so we're going to actually use printable least squares, projected least squares, sorry, to project onto components, but using the Ys, using the response variables to help us in that process. And it turns out that that's really the right way to do it. And in doing so, we actually reveal a nonlinear latent factor structure with the deep learning, which is very interesting because after all, this is what deep learning is all about. It's about revealing a nonlinear structure that can tell us and inform us about the ways in which the market and ultimately the way that the investor is performing, not just in a linear way, which is the current industry standard. So you'll be amazed to hear that pretty much 99.99% of the methodology that's used in the investment management industry to measure an investor's performance, to track exposure is all linear. It's unbelievable. There doesn't seem to be this notion that nonlinearity is important, yet it's extremely important for capturing nonlinearities. And we can see that right now. This is actually what we're going to build up to in the talk. But what we're able to do with our model is at any point in time when we fit the model, we can break down the model itself into its constituent parts. Its exposure to different latent risk factors, which are statistical risk factors, which are responsible for driving the risk premium. And we can see in sort of normal market times that these latent factor models, these latent risk factors are, which are linear, explain a lot of the returns. However, as soon as there's a large outlier in the returns, these quadratic and even higher order terms kick in. And so there's a lot there that in traditional investment management models, factor models, would not simply capture. And there would be no way of identifying what is exposure to a latent risk factor and what is something that's very unique to the portfolio itself. So this is for a portfolio of 40 instruments rather than the entire market. And these are monthly portfolio returns. So our goal here is, of course, on the one hand, to get a great prediction, but more importantly, or just as importantly, we want to understand how the model, if you can call this interpretability in a sort of economic sense, rather than in a sort of computer science sense, how the model is attributed to various different components in the linear, quadratic, and the intercept. And so we were quite surprised to see that, that quadratic and high, especially quadratic, is very important. And so that's something that, of course, we weren't surprised, but that sort of essentially negates the entire sort of last 30 or 40 years of linear factor models, which just assume linearity, or they deal with the nonlinearity in a very strange way that doesn't map onto the risk factors. So there's lots of literature, as I mentioned already, on comparing deep learning with other models. And as I said, our goal here is not really to show that deep learning is sort of better, but to show why we need the combination of projected least squares and deep learning. So let's get into what projected least squares is in a sort of short amount of time. I'm not going to have a great deal of time to explain everything, but the general setup for us is we're going to assume, and I'll get to why it's more involved than this, but let's start by assuming that what we're trying to do is a nonlinear multi-index cross-sectional model. So there's some set of inputs, X. These are typically the tall, skinny data, so lots of observations, relatively few number of features, but still a large enough number of features. Number of features might be 100, for example. and then the number of observations might be, say, 1,000. Now you can say, well, that's not very interesting. 100 features. We do 10 million at Microsoft in our natural language processing models. But our goal here is not to show off how many features we can use. It's more to explain the market outlier effects, and so that's doesn't really help you if you've got so much data. You can't then untangle it and interpret it. Of course, the trend is towards more factors, and the more the better for deep learning. Now, we're also going to assume here that the error itself is IID. But needn't be Gaussian in sort of the assumptions we're making. But for the most part, we're going to treat the error here as being what's known as homoscedastic. Now we can extend that, but that's sort of the setup of PLS. And the idea with PLS is we're going to project, as I mentioned before, both X and Y onto a lower dimensional space, a latent space, if you will. And so this is very different from PCA, which, if you're familiar with PCA, principal component analysis, you construct your covariance matrix from your asset returns, and then you find the eigenvectors and eigenvalues. The eigenvectors, of course, being the components with respect to orthogonal coordinate system characterized by the vectors. So your eigenvectors become an orthogonal basis vectors which span the some sort of vector space, and your eigenvalues become the components in that orthogonal coordinate system. And that does not take into account the y's, or the x's rather. And so we're taking into account both x and y when we do the projection. We're going to project y into a low dimensional space, u, and we're going to project our x into a low dimensional space, v. These u's and v's are known as the y and the x scores respectively. And then PLS performs linear regression between the u and the v. It's a multi-regression. And so the regression is inside here, but you have to estimate the algorithm with both the Q and the P. The Q and the P aren't orthogonal matrices as suggested here. They're not actually, they would be if they were square, but they're not, they're rectangular. And so you can't really call them orthogonal. There's no such thing as an orthogonal matrix, but a rectangular matrix. But you can, but they do have the eigenvectors as their column vectors. And so there is some overlap, but it doesn't quite, if you take the transpose and multiply it by itself, it doesn't give you the identity matrix. So you have to take the pseudo inverse. And so what we're going to do is we're going to now treat the mapping between U and V as nonlinear. And we're going to use deep learning to learn between U and V. So now we're learning in some lower dimensional space. And in many ways, it's rather like doing deep learning in an orthogonal projected space. So you do your orthogonal projections using singular value decomposition within the PLS, but then you use deep learning in this lower dimensional space. And that's sort of, in a way, what autoencoders were trying to do. Autoencoders are a little bit like PCA. They're trying to find some projection into lower dimensional space. But of course, the analogy can be it shouldn't be overstretched because there's projection in both y and x at the same time. And PLS is trying to maximize the explained covariance between x and y, as opposed to just the explained variance of y, which is what autoencoders and PCA does. It tries to minimize the reconstruction error in y for that code. So why is this interesting? Well, I think it's interesting because I recently read an article about how Google had developed a natural language processing model. I forget, how many million parameters there were or something in it. And then they come to the conclusion that they should use orthogonal basis vectors after all. In other words, they sort of come to the idea that orthogonal projections are actually better. A result that's been known since probably the middle of the 19th century that you can't really do much better than orthogonal. Orthogonal is the best you can do. And so you need to somehow combine projection orthogonally, but then use the deep learning to learn in between the different projected spaces. And I think this is a very powerful idea that autoencoders just didn't quite get right. If you look at PCA and autoencoders, it's quite difficult to actually find results where autoencoders are doing a lot better than PCA. And I mean by that, I mean reconstruction error. So what we're trying to do here is combine singular value decomposition and projection with deep learning. And so the goal here, as I said, is to minimize this or maximize this explained covariance. And I know that we sort of don't want to go into too much depth here, but the essential idea with the algorithm is to shrink along the directions which are least important. And so what it tries to do is it tries to shrink the method itself. You shrink its mechanism and find the eigenvalues and eigenvectors, but in a nonlinear way. It tries to do it using the response variables as well. And so what you end up getting are these shrinkage factors for each of the input. These are the input variables here. And if the value is above 1, it means that the response variable was useful in determining that in determining that projection or that shrinkage onto that component. And so it turns out that if the plot was entirely below this line here, then we would essentially have no reason to use PLS. We could just use PCA and there would be no gain, or just use an autoencoder or something. So this is telling you that there's additional gain over using an autoencoder or PCA. And I'm saying here because linear autoencoders are mathematically equivalent to PCA. And so without getting to all the details here, we're going to use the shrinkage mechanism, combine it with deep learning, and this theory that essentially says that we can swap out the part of the linear estimation method with inside PLS for deep learning, and it doesn't actually matter. It doesn't change the actual estimate of the U and the V's, the scores itself. It changes how sharp the estimate of the coefficients are, and also the quality of the prediction. But you can swap out the estimation procedure with a deep learning one, and it doesn't matter. So that's good. So we're going to move on now to the results, and we're going to look at linear factor models to start with. And we're going to, first of all, look at the problem of fundamental factor modeling. And the first thing to point out is that this is actually not regression. Even though it looks like regression, the core setup for factor modeling is not regression or linear regression. We do not know the B's and we do not know the F's. B's are known as the factor exposures or factor loadings, and the F's are known as the factor realizations or latent risk factors. And so neither of those are known. We know the asset returns of the ith stock in any period, but we don't actually know the B and the F, the exposures and the realizations. So one approach which Barrow took, and it's also an approach used by Fama Macbeth, is to instead proxy the exposures, the loadings for observed characteristics, in this case, firm characteristic, lagged firm characteristics. And so we're making the approximation here, it's a big one, that loadings should be one and the same thing as firm characteristics. These firm characteristics are things like book to price, size, total assets, etc. Right? But those are actually not the loadings in a more sort of fundamental sense, meaning that when we're trying to build a model to explain systemic risk factors, it's rather a bit of a stretch to say that the factor loadings are one and the same thing. And also, we don't really want these factors to be exactly the same as dimension as well as the number of characteristics, which in this case, we're assuming here that K is equal to P. Okay, so the number of factors is equal to the number of firm characteristics. What we actually want to do though is find a lower dimensional set of systemic factors. And so we can't do that in the Barrow model itself, but we can essentially introduce a model that does it in a nonlinear.
You're on mute. For some reason, you went on mute, Matthew.
Okay, sorry about that. Yeah, so we're going to write the excess returns in a nonlinear way, but we're going to now write it in terms of a nonlinear projection of these firm characteristics. After all, we have to start from somewhere, from something that we have. We only know the firm characteristics at the previous time. But we're then going to essentially find a mapping onto a smaller set of latent risk factors, and the projection of the firm characteristics are your loadings in that lower dimensional space. So the PLS gives you these loadings correctly into a lower dimensional projected space. And so that's the main idea, is that we're going to use the DPLS or the PLS. PLS does the projection mechanism. The deep learning is embedded to learn inside this, but we're going to embed this deep learner inside the projection itself. Now, I'm skipping some math details here in the interest of time, because we want to get to the results. And I can come back to sort of various extensions and so on, but there's a lot of overlap with PLS and other kinds of models that exist in the literature, which I won't get into. But we will spend some time thinking about the results themselves. So I'm going to jump to the results, and we're going to look at a set of around 1,000. So we're going to look at the Russell 1000 index over an approximately 30-year period. And we're going to take 18 fundamental factors and 31 sector dummy variables. So these are standardized dummy variables for sector, industry subgroup, etc. And we're essentially these are taken from Bloomberg. They are provided as part of the, they are provided through, you can get them from Bloomberg. That's the best way to describe it. And the basic setup is that you train in one period, you learn your relationship between your excess returns and your firm characteristics. So these B's here actually mapped onto the firm characteristics at the lag time, the lagged firm characteristics. And then you evaluate out a sample over the next period. And then you use the testing period in the next period, your training period, and so on. Now, some people said to me, well, that's just a very contrived way of doing it. You have a different model, cross-sectional model, every single time period. Why not combine it all together into some sort of time-dependent model? And I think you really lose some of the expressibility of the model when you do that. And you get much better outlier capturing if you just do the cross-sectional method. When you try to sort of take all the data into account over all time periods, you get into problems with different regimes. You then have to impose stationarity. We do not require stationarity this way of the time series. And that means the returns and the factors. And that's a huge thing, because in finance, it's a really dubious assumption that you should have stationarity. And so we can look at the advantages of using PLS for different numbers of explained variance. So these will shrink to a smaller number of factors if there's a low explained variance. And we can start to see that this is in sample, so not particularly interesting. But when you go out of sample, when we look at linear models, for example, OLS, but also lasso, it has severe problems capturing outliers. This is in part because of sort of multicollinearity, which of course can be solved by lasso. But even if you were to plot lasso, there are really substantial outliers which are not captured by the L infinity norm. This is the maximum error across the cross section of stocks in any one period. So remember, each period is a different model. There are around about 1,000 stocks in each model. The nice thing about the DPLS as well is that you don't have that much data. You have only 1,000 stocks and around about 50 factors, so 5,000 elements in your feature set for the training. And so it gets really questionable when you're building some 2-3 layer neural network, 200 neurons, why you're not going to overfit. Whereas in the DPLS, you're actually shrinking the input space, and your number of features is the number of parameters in the model is tiny. And we're going to see that in a moment. It runs about like 10 up to 100 times faster than the deep learning in the original space. And so we see big differences in the ability of DPLS to capture error. It's lower. This is the layer. It's not a great deal lower, but it definitely improves the outer sample performance. This is the average over all time periods of the uninfinity area. And we're also able to look at the performance of the portfolios over time in terms of their cumulative monthly excess returns. This is the white noise. This is OLS, a standard deep learner with 2 or 3 layers, of 3 layers, 2 hidden layers. And then these are the DPLS models. And I think the result that's the most interesting, and there's a lot of results, and we could cut this many different directions, but we see that when you look at the information ratios of a portfolio constructed of X number of stocks based on the top performing stocks, so you use the model to do the prediction, you sort in descending order, pick the top X, so the portfolio size is 10, you pick the top 10 stocks, and then that's your portfolio. And remember, this is all done now to sample. So you're predicting you're making a prediction of which stocks to hold in the next period, and then you're you're rotating your portfolio. And so there's there's stock rotation in every period as well. Now, these results, of course, don't account for fees. I'm not sort of trying to tout this as the final product that you should invest with. Of course not. It's just to show the relative gains in using DPLS versus a standard deep learner like a neural network in terms of the investment information ratios for the same data. And so that's sort of one interesting aspect. Now, we can then sort the importance of the firm characteristics as well. And that's something that we can look at. We can also look at across the different models. Another thing we can do is we can look over time at these factor sensitivities and try to understand, at what point certain factors are becoming more important than others in this sort of heat map here. Okay, and so we find this sort of outlier period here with this black line, and we can sort of zoom in and start to understand. So we can start to see if there's sort of persistence in the dominance of certain factors over time, or in general, does it tend to sort of chop and change over each period? And that's sort of something that you can do. And as I mentioned, there's huge gains as well in the computational side by using DPLS versus neural network. And of course, this goes for any problem, not just the factor modeling problem. You can use it for whatever problem you want to use. You can reduce the time substantially, the training time here for DPLS versus this is the neural network for one period only. So it can take a very long time to train the model. And so this is in seconds here. And, we can see that the number of parameters as well is quite a bit smaller here. In this one, for example, it's 10 times less parameters. So there are memory advantages as well in using this. So in summary, I know I've skipped over a lot of the sort of results and the methodology, but it's mainly just to bring to your attention the two things. Firstly, that the challenge of machine learning in finance is you can't just build a predictive model and hope for the best. You need to think carefully about casting it into an equilibrium asset pricing framework. Otherwise, it's really questionable what you're doing. Is there arbitrage in the model? How is the returns being explained by exposure to the hidden risk factors? What are these hidden risk factors? And so the PLS provides you with that information. And then Deep Learner provides you with that ability to learn the latent structure in the data itself. And so that's sort of a high level sort of overview. And like I said, there are more results coming out in the paper, a lot more results that we just haven't had time to look into. And I think the main sort of takeaway is basically that when you use a deep learner in this latent space between the scores, you learn a neural network to approximate that data in that latent space. And we know that the PLS does provide value by looking at the size of these shrinkage factors. And so that's a very interesting development that says basically that you can't use PCA if these shrinkage factors are above 1. If all these shrinkage factors above 1, you're fine just using autoencoders or PCA. So I think there's several sort of developments in this work. I've only sort of scratched on the surface, but I do think that DPLS is the right tool for investment factor modeling that no one seems to have sort of properly landed on yet. Seems to have all the right sort of adornments and functionality to make it very useful for investment, whilst being also have strong predictive power. All right, so that's my talk, and happy to answer any questions.
Questions for Matthew or for me? So we've seen today's been the factor modeling day, right? It wasn't planned, but sometimes interests converge, which is fantastic. So there's a lot of questions, guys. Okay, nothing. Anybody? Okay, so let's thank Professor Dixon for your, as usual, brilliant research, right? And very clear explanation. But thank you very much for your participation. We hope some of you can join us in the bootcamp. We're also obviously always interested in research collaborations. If some of you, after seeing some of this work, is interesting or has a good idea, we're happy to explore these things. I mean, quantitative finance is a discipline that it's full of open problems. So that's and that's very exciting, right? And obviously, deep learning and xgboost and machine learning provides a set of new tools that we can be using on this. So thank you very much, everybody. Again, thanks, Matthew and WBS, and have a nice day.
Yes. Thanks, everyone.
Thank you. Okay. Yeah. Jan has a question. Jan Dessin.
Oh, sure. I don't know.
Yeah. So one.
I'm sorry, I'm not in an easy environment. I just had a small question. When you compare the efficiency of your model compared to the traditional approach, you use MSE as a matrix. Am I right? Did I understand properly?
Who is this question for? For Gal or for me?
For you, Matthew.
Oh, yes. Actually, we use a number of different metrics. We use the L-infinity norm, which measures essentially the largest error across all stocks in any period. We do use the MSE. The MSE is not so interesting because it's really the tails there's the tail that is more interesting than the mean. And we also use R-squareds, and I haven't shown the R-squareds here, but we use different metrics. And the ultimate proof, of course, is in the information ratios, because does this lead to improved financial performance in the portfolio if you use this model? So that's why we use those ones.
Yeah, you, Jan, have asked me that on LinkedIn several times. I agree with you. Some people claims that RL can add some value just because it somehow finds a better way, right, to assess that. But certainly, as information ratio, the final outcome of it should be some sort of the answer of, okay, finally, what you're interested is in producing risk-adjusted returns, right? And the rest is narrative, so to speak, right? It's not narrative, we all know that, but we all know that. I'm not saying that it's not important what we do and only the outcome. This would be silly, right? But what I'm saying is this is also an open question as to whether when we do supervised and so on, but I think in all papers you finally assess things with information ratios or sharpe ratios, which is also an imperfect measure if you think about it, because it's just a standard deviation, and you can also argue that standard deviation it's not a good risk measure, right? And you should be using CVAR and all that stuff, but yeah, these are
CVAR
really
is very complex because basically CVAR is not stable enough. What is quite common, and for example, what is imposed in Europe when you sell a product to retail is to use the Cornish-Fisher expansion. No, it's true that the Cornish-Fisher expansion has some domain of validity, but for assessing stock return, most of the time you are well within the domain where the Cornish-Fisher expansion is efficient. When you have structured product with embedded options and so on, then it becomes more problematic. But indeed, sharpe for Sortino is not. It's just based on the Gaussian distribution. Huh?
Yeah, this is also a great debate. So CVAR is better measure than, but CVAR has lots of estimation problems, obviously, because you're looking for outliers, right? And outliers are going to be sparse, right? So, so there's a lot of, but thank you very much for, these great question. And anything else, right? And
I'm waiting for the paper and I will read it with high interest, definitely. Thanks a lot. Thanks so much for the talk, for the speech.
Thank you for your question, Jean.
Yeah.
It looks like we have some more questions, Miquel. We have a question from Pankaj. We also have a question from Manuel. I think Manuel is used. Is that for Miquel or for me?
Manuel was optimization.
What optimization? I mean, it's using a PLS algorithm so it's trying to optimize the explained covariance between X and Y. That's the PLS part. And then deep learner is just using stochastic gradient descent inside it. So it's separate. So there's theory that says that you can separate those out. And then for the question around convexity, well, you just take a Taylor expansion of the deep learning method. And therefore you have the linear part as the first term, and then you have the quadratic part, which is the Hessian term. And that's the quadratic. So it's all done with a Taylor expansion. Once you've learned the model, you can then break out the different parts into linear, quadratic, higher order terms.
Any other question? Okay, so thank you very much again. And thanks everybody. Thanks Matthew and the organizers. And see you very soon. Thank you.
Thank you so much. Have a great day. Bye-bye.
Thank you. Bye.